Okay, so starting again, what is the function family here? Quadratic or square, whichever you want to write. What is the vertex, please? 3, 2. As a point, right, with parentheses and a comma. What's the axis of symmetry? X equals 3, right? Not just 3, but x equals 3, because 3 is just 3. What's the domain here? All real numbers, and if we were writing that in interval notation, what would that look like? Negative infinity to infinity with parentheses. And what's the range?
3 to infinity.
2 to infinity. And then the 2 gets a bracket. All right, who had that right on paper or in their head? Okay, very good. This is just about a half a review of the stuff we went over yesterday. Any homework questions? Who did the homework? Okay, it went really fast, right? I mean, it's like a lot of stuff, but it's all easy. So any questions on this page? Any questions on this page? Okay, excellent. We are going to move into transformations today. We are going to actually be transforming some graphs. Only one transformation at a time today. Tomorrow we'll do multiple, and things get a little more interesting at that time. But today just 2. So here are it's like a pirate. Here are our parent functions. What we're going to do today is talk about all the different kinds of transformations you can do on a function. So this right here is what we call general form, and there's lots of stuff going on here. This is a representation of the different ways you can change this basic form of just f of x, okay? You could take the x and subtract or add something to it. That's one kind of transformation. You could add or subtract something on the outside of the function, and you could multiply by a constant in front of the function, okay? So something can happen in front of the function, something can happen right next to the x, and something can happen on the outside. And we're going to talk about how that changes the parent function, okay, from its original position. So the first one we'll talk about is the h. So you'll find the h inside being subtracted from x. Sometimes it's being added, but remember that's still kind of a subtraction because it's minus a negative, bless you. This means, so one thing I do want to remind you about for h, it will be either under the square of the cube root, or in parentheses, or inside the absolute value. It's going to be inside whatever's going on with your function, as opposed to the outside of it. And this is where the insider's lie rule comes from. So whatever's going on inside, you're going to be doing the opposite of that when you shift your graph. And so this h represents a horizontal shift, because horizontal is left to right. That's your x values. And that's what's happening here. Your x values are being changed. So if there's ever something ever happening here, you're going to change it either left or right, and it's an insider's lie move. So you'll be doing the opposite of whatever that shift is. So we have this example. This is the absolute value of x plus 3. What is the parent function for this? Absolute value of just x, right? So what I like to do is graph the parent function with just some dotted lines. So remember our pretty points from our booklet for absolute value, 0, 0, 1, 1, negative 1, 1. I'm just going to put some dotted lines here to illustrate that that's not actually my answer. It's just where I'm starting. So this change to the parent function, this was my parent function. The change is that there's a plus 3, and it's right next to the x on the inside of the absolute value. So this is an insider's lie. So a plus 3 means my actual transformation is everything going left 3. So you can do that a few ways. You can take all 3 of your parent points and just count 3 places to the left. And then connect them. But what I generally like to do, especially if there's only one transformation going on, I just take the vertex, or the initial point, or the inflection point, whatever that important point is. I just move that, and then I just tell myself, okay, that had to go right one, up one, left one, up one. And I don't actually even count the other ones. I just sort of fill it in the way I know it's supposed to look. It's like I just shifted my origin. Yes, sir. You know, I'm really good with 3. I'm good with 3 main dots. I think sometimes other teachers want at least like 4 or more. I'm really just good with 3. Because if we just want the general form here. All right, any questions? We're all good with that, right? All right. All right, the next one we're going to talk about is A. A is on the outside of the function. It's in front, just like ax squared plus bx plus c. It's a constant. And what that is doing is changing your y values, because it's a times this thing right here. And what I want to remind you of is f of x represents your y values. So it's like this is kind of like your y, and you're multiplying your y values by whatever a is up here. Now, if a is less than 1, so let's say it's a half, you're taking all your y values and cutting them in half. Okay, so if this is your x-axis and you have a y value here for your parent function and you cut it in half, it goes down lower. And the visual outcome of that is it will make your graph appear wider and squatter, like shorter. Short and wide, okay, if a is between 0 and 1. But if a is greater than 1, it stretches your graph vertically, because you're taking each of your y values, like let's say you had a y value of 1 right here, you multiply it by 4, now that point is way up here, so it stretches your graph. And if a is negative, it reflects over the x-axis. So if a is negative, you have a times whatever your function is. If it's a negative value, it's like taking a negative of your y value. So if you had this parent graph, you're taking each of these y values, making it negative, brings that y value down here. And so it reflects over the x-axis. So that's what it means to reflect over x, and that's when a is negative. So we have this example, negative 2x cubed. The parent function is x cubed. Your 3 pretty points for that are 0, 0, 1, 1, and negative 1, negative 1. And remember, this parent function looks kind of snaky. Now for that a value out front, there's kind of 2 things going on here. There's a times 2, which is a stretch, and there's the negative, which is a reflect over x. But in this case, for that a value, we can actually take care of both of those at the same time. And here's what's going to happen. My x values are going to stay the same. I'm going to take my y values and multiply them by negative 2. So the x values are staying the same. The y values are getting multiplied by the a value, which is negative 2. So my parent points are 0, 0, 1, 1, and negative 1, negative 1. So if x is staying the same and I'm multiplying y by the negative 2, well, this point doesn't change at all, because 0 times negative 2 is still 0. So that point just stays. For 1, 1, x stays the same, but the y times the negative 2 is now negative 2. That's both a stretch by 2 and a reflection that's negative. So this point 1, 1 now becomes 1, negative 2. It reflects over the x-axis and is stretched because the value is doubled. And then same thing for that third point. X stays the same. The y value times negative 2 becomes positive 2. So this becomes negative 1, positive 2. So this point goes up to here. And then we connect them. So when you have an a out front, you're taking your y values, multiplying it by that constant a. But your x's stay the same. Do we need that up anymore? Okay, so now we'll talk about k. K is on the outside of the function. So this will never be insider's lie because it's not inside anything, right? It'll always just be exactly how it looks. And this is a vertical shift because you're pretty much taking whatever your y value is, your f of x. You're taking your y and you're either adding or subtracting a value to it. So it's either going up or down. So this is x squared minus 5. Let me show you the difference here between this and insider's lie. This is different than this. Sorry, I don't know where the 2 came from. I was making stuff up. Okay, these are 2 different things. This is an insider's lie. It's right next to the x, and it'll go to the right 5. This is outside the function. This minus 5 is not inside, so that is a vertical shift. You're taking your y values and subtracting 5. So here's the parent function is x squared. So my parent points 0, 0, 1, 1, negative 1, 1. And I'm taking each of those and I'm shifting it down 5. So I like to sometimes think of it as I'm just shifting my vertex down, and then I fill in the other points. I know it's supposed to go over 1, up 1, left 1, up 1. There's my transformed graph. All right, and here's our last one we want to talk about. Excuse me. We want to talk about when the actual x is negative, not the a out front, but the actual x. So it would be inside the parentheses or the absolute value or the square root. There'd be an actual negative sign right here, right in front of the x. When that happens, you're now reflecting over the y-axis. And let me tell you why. Why? So if you have some point here on your original graph, and you're taking the x value and making it negative, so now that exact point is just going to be over here. So whatever your graph here is reflects over the y-axis. So now the y-axis is like a mirror, and that point reflects over when your x is negative here. So here's an example of that. So we have absolute value of negative x. The negative's on the inside, right in front of x. The parent function is 0, 0, 1, 1, and 4, 2, because those are easy square rootable points. The y values are staying the same. It's the x value we're taking the opposite sign of. So 0, 0 doesn't change. But this 1, 1, the x becomes negative. So now it's negative 1, 1. So we're changing the sign on the x value only. And then 4, 2 from the parent function, we're just taking the opposite of x. So that becomes negative 4, 2. Okay, see how it reflects over y, because you're just making x on the opposite side. Is that our last thing? Is that our last thing?